Hello everyone and welcome to this lecture. In the last lecture we saw a very beautiful application of incidence matrix. Okay, we find the number of spanning trees using it. In this lecture we will see some more applications of it. Okay, but before that I need some warm up on matrix terms, like what do you mean by linear combination of vectors, linear dependency, linear independency, and what we mean by rank of matrix. I know most of you already have covered this in your basic linear algebra course, but before proceeding to the applications of matrices, it's always good to have some kind of warm up. Okay, so let us start with the warm up and then we will proceed with the applications of incidence matrix, few more applications. Okay, so let's suppose we have some vectors v1, v2 up to vk, and suppose all of these vectors have k coordinate, n coordinates, so n entries are there, so suppose they lies in Rn. Okay, so what do we mean by linear combination of these vectors? Linear combination is nothing but what you do, you scale these vectors by some scalar quantity and then add all these vectors. So suppose this is suppose I multiply v1 by lambda alpha 1, v2 by alpha 2, and so on. So this will be giving us a linear combination of these vectors, and of course this will be equal to some vector, so let us call u. Okay, in this setup we call u can be written as a linear combination of vectors from v1 up to vk. Okay, sometime it is not possible, to write a vector in terms of linear combination of given other vectors. Okay, so for example let us take a 2D case, 2D plane here. So suppose I draw this vector v1 and this v2. Okay, so no matter how much you scale one vector, you cannot write other vector in terms of it. Okay, but if you take three vectors, you can write any of these vectors in terms of linear combination of other two. Okay, so just it is for you to check again, a DIY why it happens. Okay, very simple observation. Okay, basic linear algebra stuff. Yeah, very good. Yeah, and then okay, so in this setup, when so suppose this, when you cannot reach or you can not write a vector, so like here you cannot write v1 in terms of v2, we call that these two are linearly independent. Here it is linearly independent. I will formally define it shortly. Independent, this is just a pictorial thing, linearly independent. I hope the spelling is correct. And these set of vectors, set of these three vectors is actually linearly dependent because you can write as a linear combination. Okay, linearly dependent. Very good. Okay, we call the vectors v1, v2 to vk as linear independent when the linear combination implies that all of these alpha i's are all are 0. All. That means you cannot write any vector in terms of set of any other vectors. I mean among these vectors you cannot write them as a linear combination of each other. This implies that. So this set is linear independent when all you are not able to find some non-zero alpha i's. Otherwise this set is dependent, linearly dependent. Okay, very good. You just check, you take any three vectors in 2D plane, they have to be linearly dependent, and in case of two vectors sometimes they are dependent, sometimes not dependent. Like here they are independent, but you may also frame two vectors which are actually dependent. Okay, so let me actually put that picture also. In this case, if you see, suppose one vector is overlapping with other. Okay, overlapping. Basically you are writing a vector in terms of scaling of other. Okay, so this is linearly dependent. So these two vectors are linearly dependent. Okay, very good basic stuff. Okay, now let us move next to what we mean by rank of a matrix. Okay, so again, many times you must have heard this term. So suppose we have a matrix of n cross m. Okay, and suppose this matrix is a11 up to a1n, an1, anm. So this will be m. Okay, there are m columns. Okay, now what is rank? Okay, so rank is, you might have heard of this thing, oh, rank is number of linearly independent columns. Okay, in fact the correct statement is the maximal, a set of maximally linearly independent columns. Okay, so basically rank is nothing but, rank of A is size of, or the number of vectors in a maximally linearly independent number of vectors in maximally set of columns. Okay, now you might be wondering why this definition, why only we care about the columns, right? Why not rows? Because rows are also vector, right? They are lying horizontally, so these are also vectors, right? Very interestingly, these two things are same. So if I safely can call this as column rank. Now let me define what row rank. Row rank is, row rank of A is same as this. So number of vectors in a maximally linearly independent set of rows. Now the thing is, why we call rank? Why not, oh, that was the column rank, this is row rank? We call it simply rank because these two quantities are always same. So this is your first, in fact now second DIY for this lecture. So column rank of A equal to row rank of A equal to, and that's why we simply call rank. DIY. This will help you to revise your basic linear algebra when you try to solve this. Very good. Okay, very interesting fact, very neat fact. Okay, now let us move to the relation between various linear combinations associated with matrix. Okay, so let me take the same matrix again. Okay, same matrix again. No need to actually expand this matrix. Okay, so suppose this is again M cross N matrix. Okay, what happens when we multiply a matrix with a vector? Suppose a vector here. Okay, x is of dimension, there are m entries because A is of n cross m. Now this is necessary in order to define the product. Okay, so this will give you some other vector, right? Y. Remember, y will be in Rn. So x will be in Rm. Okay. Now we want to find some special vectors x such that when we multiply it on the right of A, it will give you 0. So we want basically something which gives 0. Okay. Collection of such vectors we call null space of A. Okay. Null space of A equal to collection of all such vectors such that Ax equal to 0. Ideally, I should say this as a right null space because I am multiplying x on the right of A. Okay, but okay, so to be very clear, let us write right null space of A. Okay, similarly, there can be you can multiply the vectors towards the left, right, but this time this will be a row vector. So something basically this. Okay, by the way, in this whole course, by mean of vector I will always take as column vector. So like this. okay, x2 up to xn, and whenever I have to use this as a row vector, I will just take simply transpose. Okay. Now similar to right null space, there is something called left null space. We can call left null space of A. Very good. So what it will be? It will be again collection of vectors such that if you multiply the vectors toward left, so basically x transpose A will give you 0. Remember, this 0 is now a 0 row vector, right? Earlier this 0 was a 0 column vector. Okay. Now yes, what? And this is actually same as, if you take transpose of this, is same as A transpose x equal to 0, same as. Okay. So this is left null space. Now why I am interested in all this? Okay. I want to find the maximal number of linearly independent set out of this set, right? This number of vectors in that maximally linear independent set we call nullity of this, nullity of A. Nullity of A equal to the same, the number of the number of elements or number of vectors in the maximally linear independent set of null space. So this we call nullity. I am not writing it, so I hope you got what I said. Okay. So now there is an interesting result. There is a very interesting result which relates the nullity of A, rank of A, and the number of columns in A. This we call rank nullity theorem. This is equal to basically rank of A plus nullity of A is equal to what with the number of columns is equal to here. Very good. Ideally I should write here to be safer side, because nullity I am taking from right null space, so maybe I can write as right nullity. Okay. Similarly, the famous thing can be written for the rows also, and that thing is rank of A. Remember, row rank and column rank is same, so I am just writing rank, right? This is DIY, you have to prove why it is so, plus left nullity equal to n. So this is also DIY, this is also DIY. Okay. Please revise this beautiful fundamental concepts. Okay. And so let us now move towards the applications of incidence matrix. Very nice. I hope I have covered. Yes, very good. All these things are sufficient for us. Okay, great. So let us proceed with our first result. Okay. The first result is this. Yes, so let me call it theorem. Spelling of theorem is correct. Okay. Let G be a graph on n nodes or n vertices graph, then it is connected if and only if what? The rank of the incident matrix of G is equal to n minus 1. Okay, just by looking at the rank of matrix, incident matrix, you can actually determine whether the graph is connected or not. So let us prove this. So we have to prove it both ways. Okay, so let me proceed with, so suppose graph is connected, then we will establish that rank of QG is n minus 1. So let us move towards the proof. Okay, suppose G is connected. I hope what we mean by connected. So there is a path between any two vertex, right? Okay, so in this case, let us write down the incident matrix. So QG will be, so this will be some matrix, right? So there will be edges. Suppose there are m edges. Okay, and they are 1, 2, 3 up to n vertices. Okay, so this is n cross m matrix. Very good. Now when G is connected, okay, now I have to actually find the rank of this matrix, right, given that G is connected. So in order to find the rank, I will be using either this basically this equation or this equation. Okay, so let us use this equation. Okay, I will try to find what will be in the left null space or what will be the left nullity of A. In that way I can safely, because if I know this quantity, I will just remove, basically then I have to prove n minus rank of A. Okay, so n I already know, so in that case I will be knowing what rank will be. Okay, so let us see what will be in the null space. Okay, so let us write this quantity. So let us find what will be the null space, what will be in the null space of this. So we want to find x such that it is giving you 0 0 0. So how many zeros? M zeros, right? Yeah, I mean, yeah. So this is a row vector. Okay, very good. So now okay, so how will we find this? Okay, now so let me actually expand this. So suppose x is your x1 x2 up to xn, so it will be clear in a moment. So what this product will look like. Okay, so x1 x2 up to xn, right, how many elements? Yeah, so this will be xn. Okay, so now if you see that in each column here there are +1 or -1 in the incident matrix. Recall the definition, right? -1 +1 and rest of this place there will be zeros, right? So in this way, this. Okay, so whenever there is an edge xy, suppose between between vertex I and j, vertex I and suppose there is an edge I and j. Okay, so there will be some vertex I, some vertex j corresponding to this vertex. Suppose there is an edge. Okay, so there will be somewhere corresponding to it will be 1 and corresponding to it will be -1. Okay, otherwise it could be vice versa also. Here it could be -1 and here could be 1. Just definition of incident matrix, right? Now when we multiply this vector, okay, with this matrix QG, okay, recall that whenever, suppose this is your vector, this is your ith row, this is your jth row, the corresponding here will be either 1, here will be -1 or -1 or 1. Okay, when you multiply this vector with this column, okay, and rest of the entries are by the way 0. Okay, so what will be the equation? And this is giving you zeros, this is giving you 0, so all zeros basically. Okay, so this equation gives you, whenever there is an edge, right, between I and j, this will give you xi minus xj equal to 0 or x minus xi plus xj equal to 0. In both the cases this implies I equal to xj. Now what next? Now since graph is connected, this guy will have also edge to some other vertex and so on, keep on going, similarly this and this, right? So this imply every coordinate since G is connected, this implies x1 equal to x2 and so on equal to the number of vertices, right, xn. Okay, so basically the structure of x, whatever is in the null space, all these vectors will have this same, all the coefficients are same, coefficients or entries are same, right? Now what we need to find is there, so basically at most one linearly independent vector is there, okay, but can we find one linearly independent vector? If you look at it carefully, in fact this is, I mean, it is very clear that if you just do this 1 1 1 all one vector, okay, if you multiply with qg, this is indeed giving you 0. Okay, so all one vector is in the null space of this, right? So that means the rank of qj is, now we have established that rank of qg is n minus 1. Okay, let me recall what I said. So we try to find the null space of this. The null space say was coming out to be this. Okay, that means basically whatever the vector will be, the all entries are same, right? It could be 0. If that was the only solution, 0 was the only solution, in that case the rank will be n, right? Because in the null space there was no, there was no non-zero vector, right? But fortunately we have a vector which we call all 1 or just a scaling of all 1. Okay, so that vector is in the null space. So there is one independent vector which is all 1 vector, or it's a scaling version. Okay, so that's why the rank will be, so yes, from here you can see that the left nullity will be 1. Okay, and hence the rank will be n minus 1. Okay, very good, great. So we have established this. Now what about the converse part? What about the converse part? Converse part is this. Converse part, yeah. So now suppose rank is Qn is Qg n minus 1, right? Then we have to establish that the G is connected. G is connected. Okay. So we will, this is also straightforward. We will use a technique of contradiction to prove that. Suppose G is not connected. Suppose G is not connected. Okay. In this case, there will be at least 2 components, right? Suppose this is one component H and this is rest of the component G minus H. Okay. Now what your QG look like? QG will be looking like here. Now by now I hope you must have got what will be the shape like this. So this will be somewhere the incident matrix of H, and there will be the incident matrix of G minus H. Okay, all the entries here will be 0. Why? Because any vector, any vertex will not be falling into any of the edges here, right? So all these entries. Similarly, any of the edges here are not falling into any vertex here. So this will be also 0. Okay, what will be now? It is given that the rank of this QG is n minus 1. This was given to us, right? Now let us try to find the null space of it again, left null space of it. Like we proceed in the first case, if you see carefully, if you multiply, so we want to find the null space, right? So if you see this vector where these are all 1, 1, 1 up to how much time? Suppose in H they are k. Suppose the number of vertices in H are k. So suppose these are k ones, all one vector of size k, and rest of these are 0, 0, 0, 0, 0, 0. So how many times 0? So n minus k. Okay, n minus k, and you just multiply with QG. Okay, what will happen? This will give you, it's just very small, simple exercise. This will give you 0. Why? Because this 1 will be multiplied with this, and each column there is 1, 1 and 1 minus 1. So summation of these will be equal to 0. Okay, so this will give you 0. Okay, and this 0 will be multiplied with this, so it doesn't matter. Okay, so everything will be 0. Okay, that means this vector, call it suppose V1. This is in the null space of QG. Okay. Similarly, you can also cook another vector. That vector will be this. Okay, so that vector will be 0, 0 up to 0, and then again 1, 1 to 1. These 1 now are n minus k times, and this will be k times. Okay, this will be k times. Now you see that this vector will also be giving you, when you multiply with QG, this will also be, okay. So we got 2 linearly, now these 2 are linearly independent vectors. It's very easy to see, right? Wherever there are ones, there are zeros here, right? So you cannot, by scaling this vector, you cannot reach to this vector. So linearly independent vectors. So we got 2 linearly independent vectors. Okay, not to confuse here that, oh, why you have assumed that there will be, oh, I mean, this will be also connected, right? This will be, I mean, this could be disconnected, but still this argument will also work, right? This will it still be giving you 0 when you multiply with qg minus 1. Similarly here. Okay, so these two are independent vectors. So there are at least 2 independent vectors in your null space. So your rank will be, by rank nullity theorem, the rank of A will be at most it will be always less than n minus, always at most n minus 2. Yeah, at most n minus 2. Okay, at most n minus 2. But what is given to us, rank is n minus 1. But it said it could be at most n minus 2, it will never reach. That means our assumption that G is connected is false. So that means, so sorry, our assumption that is, suppose G is not connected is false. That means G is connected. This implies G is connected. Contradiction, let me write. So this is contradiction. Very good. So I hope you got the proof idea. Very simple one, but very important as we proceed with these more lectures. Okay, so very good. Yeah. Now the final theorem, or rather it is a corollary. So corollary is this. What will be the corollary? Yeah. So let G be a graph on n vertices, then rank of qg equal to n minus k if and only if what? If and only if there are k connected components, or simply components, k connected components. Very nice. Yeah, proof is actually straightforward once we know the proof of this. So yeah, very good. So proof is what? So what will be, so suppose there are, I mean, we can proceed with so let us write what qg will look like. Suppose there are k components, right? C1, C2 up to Ck, okay, and each of them has, suppose, the vertices n1, n2 up to nk. So these are vertices, number of vertices is spelling is, yeah, good, I. Okay, good. So now what the incident matrix will look like? So qg will look like this. Now it is actually very easy to see. This will be q c1, q c2 up to q ck, and everywhere this is 0. Okay. Now the rank of this qg is what? Rank of qg is nothing but will be rank of qc1 plus rank of qc2 and so on, plus rank of qck, which is in fact from the previous theorem. This is nothing but n1 minus 1, n2 minus 1 and so on, nk minus 1. Okay, the sum of all ni's is nothing but equal to n, and how many terms is minus 1 is coming? K times, right? Okay. Now why this if and only if thing is happening? So see, this if and only if thing is happening from actually the previous theorem. So this part is equal to n 1 minus 1 if and only if the graph is connected. Similarly, this part is if and only if this, I mean everywhere the chunks are connected, right? And then only the rank is n minus 1, right? So this is, in fact, this is true that the rank of qg is then n minus k if and only if the graph has k connected component. Okay, so this was all very straightforward result. Now before ending this lecture, I want to give another DIY, just simple fact, prove that the same thing happens for Laplacian matrix also. Basically, so DIY is this. a graph has k connected components if and only if the rank of Laplacian matrix equal to n minus k. Very good. This you have to prove. I mean, the hint is the obvious one. L you can write as q into q transpose and then take properties of rank. Okay. So thank you very much and see you in the next lecture.